So now we want to prove Kuratowski's theorem. For that, we first prove this lemma. What does this lemma say? If G is a graph with the smallest possible number of edges among the all non-planar graphs having no Kuratowski subgraph, then it is three connected. So what does it mean is that if we want to prove Kuratowski's theorem, and then assume that we have a minimal counterexample, then that minimal counterexample, if it exists, it has to be direct connected. So that's what it says. And assume we have such a graph G, then when we have this graph G, once we delete one edge, now it has a pure number of edges. And then deleting does not create a K5 subdivision or K33 subdivision. So that's a pure number of edges, which still does not have any K5 subdivision or K33 subdivision. Then by the minimality here, that means G minus E is a planar graph for all E. That means G is a minimal non-planar. So that the previous lemma said that the G is two connected. Okay, so if G is not three connected, then since this is two connected, we can take the separating set of size 2. Then what? And now we use this lemma. This lemma we prove. We have a separating set, and one of the slope plus h between x, y has to be non-planar because the original graph is non-planar. Says G is non-planar. G prime union with x, y is non-planar for some slope G prime. So what do we have? X, y. We have a slope G prime here, and then there must be another one because this is this is a coset, and because you cannot separate this by using set of side 1, that means x and y sends at least one edge to here and at least one edge to here. Then what? If you take the G prime and then add one edge between x and y, and this G prime has at least two less edges than G, because this edge is lost. So if we take this G prime union with xy as H, then this H has fewer number of edges than G, and this also lacks the H5 and K5 subdivision or K33 subdivision. Minimality of G forces H to have a Kuratowski subgraph. Sorry, so what I previously said, the syntax was wrong. So minimality of what do you know? This is non-planar. H is non-planar, right? And H had fewer number of edges than G. But what was G? G was the fewest edges among all non-planar graphs having no Kuratowski subgraph. So if H has no Kuratowski subgraph, then that's also non-planar graph, and that has a fewer number of edges than G. It's a contradiction, right? Then the only possible case is H must have a Kuratowski subgraph. That's still possible because we add x and y. We add h between x and y to obtain h. So this G prime, this h is not a subgraph of G. So G have no Kuratowski subgraph, but h could have Kuratowski subgraph, for all we know. But we want to prove that that's impossible. So let's say this Kuratowski subgraph is F. All of F appears in G, possibly except the HXY. So if you have F in here, then you must use this HXY. Otherwise, it's a subgraph of G, which is contradiction. G does not contain a Kuratowski subgraph. But since its S is a minimal vertex point, it is two connected graph. So vertex called size 2 is minimal. Both X and Y have neighbors in every S loop. Thus what? Instead of taking this edge, we can take this path through some other S loop G double prime. Thus, we can replace XY in F with an XY path through another S loop to obtain a Kuratowski subgraph. So, but what we assume? We assume that G has no Kuratowski subgraph. This contradicts the assumption on G. So this G has no separating two steps. And 3 connected. So this proof. Okay, now what? So our plan is that assume there is a minimal counterexample for Kuratowski theorem. Then previous lemma said that that's three connected. This is 3 connected. And I mean, we know that there exists 3 contractable H, XY. And what we do, we consider G contraction XY. We contract X and Y. Then we want to show that this has no Kuratowski subgraph. If this is true, then what? This is smaller graph having no Kuratowski subgraph. And then our G was minimal counterexample to Kuratowski theorem. So this is not counterexample for Kuratowski theorem. So this has to be planar. So we can embed this. So this contraction, X and Y become G. And there is some way to embed it. And then what? Based on this embedding of G contraction X and Y, we make some modification to find the embedding of X, G. That's contradiction because G was a non-planar graph, so which was the minimal counterexample. So this is our plan. For that, we have to show this. So lemma, if G contraction X and Y has a Kuratowski subgraph, then he also has a Kuratowski subgraph. So let's prove it. So let H be a Kuratowski subgraph which is either a subdivision of K5 or a subdivision of K33 in this smaller graph, and let G be the vertex of this obtained by contracting xy. So if C is not in H, then what? H is a Kuratowski subgraph. Of G. So we are done. And what? If G is in the vertexes of H, but G is not a branch vertex, then what? In this H, let's say this is G, then in the original graph, how does it look like? In the original graph, wait, what? Sorry. I clicked something wrong. Wait. Okay. Yes. In here, in the original graph, how does it look like? One of the two things. So either one of x and y plays the role of G, or this G, so okay, let me say in this way. G had a neighbor here, say U1, U2. So this is U1, U2. Then either U1, U2 both are neighbor of X or both are neighbor of Y. Then we obtain a Kuratowski subgraph like here. And if U1 is neighbor of X and then U2 is neighbor of Y, then simply you replace this path with one longer path. Then this yields, then we obtain Kuratowski subgraph of G from this H. I replace this G with X or Y or the X, XY. And in the similar way, if C is a branch vertex, in H, and most 1H is instant, 1H instant to G. So in G, so there are many edges instant to it. And in the original one, only one edge is instant to Y or X, one of the, say, let's say X. Only one edge instant to G is instant to X in G, then expanding G into XY, it just lengthens that path, and Y is the corresponding branch vertex for the Kuratowski subgraph in G. Simply, from here to here, it's same as just subdividing this edge. right? So if out of those edges, these are distributed between x and y here, and if only one of them is here, instant with x, then it's the same as taking subdivision one time. This edge is subdivided. Then it was the Kuratowski subgraph in G. And in particular, if H is K33 subdivision, then what happens? Then G is adjacent with 3. So in X and Y, 2 of them is here and 1 of them is here. And potentially, okay, there could be more, but I mean, more in the graph G, but among the edges that's corresponding to H is out of these 3, however you distribute it, there are one of them contains either 1 or 0. So then we are done. So in the remaining case, H is K5 subdivision. The only possible case is G has these 4 edges, and then in X and Y, you have 2 and 2. It's well distributed. See the branch vertex of H, and both X and Y are instant in G to 2 of the 4 edges instant to G in H. Okay, and X and Y, and then in the original this H, this H is the beginning of some path which goes to say U1 and U2, B1, B2, and that forms a subdivision of K5. So we let U1 and U2 and B1 and B2 be the branch vertices of H at the other ends of the path which leaves G1 edges instant to X, and yeah, those 2 are the ones you get from here and here. This edge incident to X, and then B1, B2 are from Y. Then what we have? This H, now you have X and Y, and somehow it goes to U1, U2, somehow it goes to B1, B2, and there are passes between these and these, and these and these, and these and these. I have drawn this way so that you might think that there is a crossing, but these are drawn in without crossing. Okay, so it's not drawn, it's just a graph. So what I said was confusing. So there are, these passes are disjoint. They are vertex disjoint, and then edge disjoint. Yeah. I mean, technically, this share the endpoint, but they are only sharing the end vertex. Now what? In here, we just forget the last path by deleting the U1, U2 path and B1, B2 path from this H. We obtain K33 subdivision in G, in which is Y and U1 and U2 are the branch vertices for one partite set, and X, B1, B2 are the branch vertices for the other partite set. So from here, you have like 3 passes to X, B1, B2. And yeah, again, from here and from here, you have 3 passes to X, B1, B2, X, B1, B2. So this gives us the subdivision of K33. This proves the lemma. So now we have what we need so that we can actually prove Kuratowski theorem. So we want to prove Kuratowski theorem. In fact, we want to prove a stronger theorem. Let's say a convex embedding is an embedding where every edge is a straight line. There is a straight line segment, and every base is a convex polygon. And that's what we call the convex embedding. And what we can actually prove is that if these 3 connected graphs containing no Kuratowski subgraph, then G has a convex embedding in the plane with no 3 vertices on the line. This, together with the previous lemma, this lemma, proves the Kuratowski theorem. Why? Assume there is a counterexample to Kuratowski theorem. Take the minimal one, and this says that this is 3 connected. However, what this theorem says that this minimal counterexample is 3 connected, and then contains no Kuratowski theorem. So it can be embedded. So it is planar. That means it's not a counterexample to Kuratowski theorem. So, there are no counterexamples. So now all we need to do is prove this theorem. So we use induction on n, the number of vertices. So base case, if n is most 4, then the only 3 connected graph is K4, and K4 can be drawn this way. So this is exactly what we want. Every base is a convex polygon. So assume n is at least 5. So this is 3 connected. So we can take 3 contractible X, as we have proved in the section of activity, such that G contract E is 3 connected. Then what? By the previous lemma, in here we show that the contraction if G has no Kuratowski subgraph, then G contraction xy also has no Kuratowski subgraph by the previous lemma. G contraction E has no Kuratowski subgraph. So the induction hypothesis implies that if H, which is G contract E, has a convex embedding, with no three vertices on a line. And let G be the dual vertex we obtain from contracting xy. So now what? We just give us a convex embedding of H. So what? In this embedding, the subgraph obtained by enriching the edges incident to G as a face containing G, which is possibly unbounded. So what? You have its face, and then G is here. Once you delete all the edges from G to G. And moreover, this face, we know how it looks like. Since H minus G is two connected, and this outside is a convex embedding of H minus G. It's the boundary of this space is a cycle AC. So this is the cycle C. And all neighbors of G lie on C, and they may be neighbors of X or Y or both in G. So what do we know? So in the original embedding, you have G, and then you have this, right? And here, this is straight line, straight line, straight line, straight line, straight line. And out of these, you see how many are actually neighbors of X. Okay, so let's say that let X1 to Xk be the neighbors of X in cyclic order on C. So this is X1, X2, X3, Xk. If all neighbors of Y lie in the portion of C from specific xi to xi plus 1. So if all the neighbors of Y lies in this proportion, including x1 and x2, then what we can do is we draw Y here, and then we draw straight line segment. That will then we obtain a convex embedding. of G by putting X at the position of G in H and putting Y at the point close to G in the wedge formed by xxi and xxi plus 1. If not, then we have one of the two cases. And either one, Y shares three neighbors, U, B, W with X, or Y has neighbors U and B that alternate on C with neighbors xi and xi plus 1 of x. So xi and xi plus 1 are the neighbors of x. Indeed, so what? If the star does not hold, then what? Y have at least two neighbors, say one in this region, then another one in other region, say here. Then this and this alternates so that the second one holds. In order to avoid the second one, it's possible that the one is in here. So Y, so this is also the neighbor of Y. So these vertices could be also neighbor of Y. And if it's here and it's here, then what? You can take this and this and this and this. You remember what? No, this and this and this and this. So you can adjust I so that the this and this and this are alternating. And if you want to also avoid that, well, the only way is taking this way, but in this way, it's still contained in this interval, so this holds. But one case we didn't consider is that if x has only 2, so note that the x and y have degree at least 3. That means except y, x has at least 2 neighbors, and the y also has 2 neighbors. And in that case, I mean, if this y sends one edge here and then one edge here, and it's not alternating, so that the second doesn't hold. But in that case, they also belong to here. And yeah. So in any case, we can check that one of these two must hold. In case 1, what? We have C, and then you have X, Y, and they share 3 common neighbors. I mean, in here, 3 neighbors. Then C together with XY and edges from XY to this UVW from K5 subdivision. A contradiction. In case 2, we have this C and then X, Y. Then what? X, Y has neighbor U and V, then XI plus 1. Then C together with the asset U, Y, Y, B, X, XI, X, xi plus 1, xy from a K33 subdivision. So you can put these three on one part and these three the other part, and what? Distance 3 edges to the red one, and distance 3 passes to the red one, distance 3 passes to the red one. So this is K33 subdivision. Sorry. This is a contradiction. So, since we are considering only graph without Kuratowski subgraph, this must hold. And in that case, this yields desired embedding of G. So this proves the lemma. So this proves, this theorem about convex embedding, and then it proves the Kuratowski theorem. And this theorem is tight in a sense that assuming three connectedness is required. For example, if you have a K24 as if it's two connected, it has no convex embedding. It's not difficult to actually check that no matter how you draw this, you will get one of the base as not convex. However, the Ferry, so there is theorem by Ferry's theorem, says that every planar graph has an embedding in which every edge is a straight line segment. The proof is not too difficult, so you can try. The main idea is that you consider the triangulation of this planar graph. Here, triangulation is you add an edge so that all the faces become triangle. And if you have an embedding of that, then you obtain an embedding of the original one. And then, you can use the fact that all planar graphs are 5 to generate. So there is a vertex with degree 5. And you can think about it more. So it's not too difficult. Anyway, so we know that such an embedding exists. Okay, so far we have learned about this planar graph, and then we show a complete characterization of planar graph in terms of this minor than subdivision. And next time we consider coloring of the planar graph. As I mentioned, when we are studying coloring, we mentioned about the four-color theorem, that whether we can color the map, the region of each country by a certain color. Can we complete the coloring with four colors so that all the, two countries sharing a border gets different color? So that's related to the coloring of planar graph. So, it has been, the coloring of planar graph has been studied quite a long time, and we will talk about that in the next lecture. Okay, thank you for listening. See you